Pythagorean theorem. So, trigonometry is all about right triangles. And so, as you might expect, we end up seeing and using the Pythagorean theorem often. And so, that's what this lesson is about. Now, we are actually not, because we've reviewed using just the Pythagorean theorem, like just using this formula. We've done that over and over and over again throughout this course. And so we're not going to do just a normal Pythagorean theorem example. We're going to look at the places where we kind of are extending it in this lesson. So this is the Pythagorean theorem. If for some reason you need a review, this is what it is. It relates the legs to the hypotenuse of a right triangle. But remember that it is a squared plus b squared equals c squared. And excuse me, A and B are the two legs of the right triangle, so they're the ones that are adjacent to the right angle, and C is always the hypotenuse. It's the one across from the 90-degree angle. Now, it doesn't matter which one. Sorry, my neck was going nutso there for a second. It doesn't matter which one is A and which one is B in the formula. It can be those are interchangeable. Okay, so next thing. Oops. So the next thing, and this is the first kind of place where we're going to extend it, is looking at a Pythagorean triple. So a Pythagorean triple is a set of three non-zero whole numbers, and that's really the key there. So A, B, and C, such that a squared plus b squared equals c squared. And so what this is saying is a Pythagorean triple is where we have all three numbers are whole numbers. So see, there's no decimals, because a lot of times when we've used Pythagorean theorem in the past, we have, we get a decimal equivalent, right? Or a reduced radical or something along those lines. But a Pythagorean triple is where all of A, B, and C are all whole numbers. There's literally infinitely many of these. There are lots of Pythagorean triples. There's three that are pretty common that we have here on this page. There's 3, 4, 5 Pythagorean triple, 5, 12, 13, 8, 15, 17, and then 7, 24, 25 are some really common ones. Now, you notice underneath that all of the ones that would be multiples of the most reduced one would also be Pythagorean triples. So like a 6, 8, 10 would be a Pythagorean triple in the form of a 3, 4, 5 Pythagorean triple, right? And that's true for any multiple. And that's what this bottom line here is, where you can do any multiple of the reduced Pythagorean triple and you'll have another Pythagorean triple. So that's what we're talking about there. And so I will note that we see this one, 3, 4, 5 triangle, all the time in a upcoming lesson, maybe even the next lesson. In the next lesson, we're going to look at some special right triangles that are even have some more particular ways. Basically, we're looking at things that we can estimate and get a good idea if we reduce things down to usable things. And so these are a few examples of Pythagorean triples. Now, the way you might use Pythagorean triple in a math homework assignment is a problem like this. Use Pythagorean triples to find x and explain your reasoning. So we're looking at this and we want to see if this goes back to any of the Pythagorean triples that we know. So is this a 3, 4, 5 Pythagorean triple? Well, let's see. If we reduce this one down by something, then we can turn it into 4, and we reduce this one down by something, we can turn this into 5. So if this one is 3, then that's good. So what could this one be, right? So looks like 3, 4, 5. So this one is the 3 ratio. So how can we solve for what x is? Well, we could probably do it in our head, but we can also just set up a simple proportion, right? We can say x to 3 equals 12 to 4. Now, we could also use 15 to 5, right? We could also kind of see what the scale factor is. The scale factor on all these is 3, so this is probably going to be 9, but let's use a proportion to verify verify our results multiple different ways. Looks like their scale factor is 3 though. So x times 4 is 4x equals 3 times 12 is 36. If we divide by 4, we end up with x equals 9, which means the scale factor between all of these is 3. Therefore, x equals 9, right? So that's the answer. That's the explanation. Let's do the next thing. So this is the fact is just saying that the converse of Pythagorean the converse of the Pythagorean theorem is also true. I didn't even do an example of here. Basically, it says if the sum of the squares of the lengths of the shortest sides, so a squared plus b squared, right? A squared plus b squared, if that equals c squared, the square of the length of the longest side, then it's a right triangle, right? Then we have a right triangle. That's all this theorem says, that the converse is true. Now, you might be saying, oh, we're not doing proofs, so why would we use this? Well, we might need to be able to say that this is a right triangle because if we know it's a right triangle, then we can use our trig ratios, which we're going to learn later. And so we may need to soft prove that something is a right triangle in order to use some other tool. So that's how we would use this converse at this point in this course. But you could also use it to prove that a triangle is a right triangle as well through our more traditional proof means. So next thing is that Pythagorean identity. Excuse me. I actually wrote that when I was prepping this file. I wrote that like 3 times before I wrote inequality. Pythagorean inequality theorems is real simple. If c squared is less than a squared plus b squared, then the triangle ABC is acute. And if c squared is greater than a squared plus b squared, then the triangle is obtuse. Let's use this in an example, and then, believe it or not, we're going to be finished with this lesson. So, determine whether each set of numbers can be measures of the sides of a triangle. If so, classify the triangle as acute, obtuse, or right. So this first part, the whether each set can be measures of the sides of a triangle, that we've got to go back in our memory and remember, right? So if we remember, in order to determine whether 3 sets of numbers can be a triangle, the sums of each pair of 2 has to be greater than the third one, right? So for determining whether it can be a triangle, is 7 plus 14 greater than 16? Well, 7 plus 14 is 21, right? Which is greater, so that's good. What about 14 plus 16? Well, that's easily going to be greater than 7. I'm going to put it here for the sake of our notes, right? So that we know what we're doing. You should probably do the same so you know what has happened when you go back and look at your notes. Is that greater than 6? Oh, is that greater than 7? Well, each of these is greater than 7, so that definitely works. And then the last one, 7 plus 16. 7 plus 16, for similar reasons, is definitely greater than 14 because 16 is already greater than 14. So it are the sides of a triangle, right? That's legitimate. So it can be measures of the sides of a triangle. Now we're going to classify the triangle as acute, obtuse, or right. So for that part, let me change my color here. So for this part, we're going to see the 2 smaller sides. Is their squares sum greater than the hypotenuse, maybe the largest one's sum? So how does 7 squared plus 14 squared, how does that compare to 16 squared, right? So we're probably going to want our calculator for this because some of those squareds are going to be kind of large numbers. So 7 squared, actually, we can do without a calculator. That's just 49. That's easy peasy. And actually, there are some tricks. If you're in like UIL number sense, you may know some tricks to be able to do 14 squared or 16 squared real quick and easy. But for the rest of us, we might pop that in the calculator and get 14 squared is 196. And we know, is that greater than or less than or equal to 16 squared? So 16 squared equals 256. 256. 49 plus 96. 49 plus 96. We probably do that in our head if we really wanted to. Oops. Plus 96 plus 100. You see what I did there? But I fixed it. 245. So 245 is less than 256. Therefore, it is acute. Triangle is acute because it's less than. All right, what about these? So, can they be triangles? That's what we're going to start with. Can it be a triangle? So, 9 plus 40. Plus 40, is that greater than 41? Well, 49 is greater than 41. So, yes, that works. What about 40 plus 41? That's easy peasy. 40 plus 41, is that greater than 9? Yes. Right? 40 and 41 are both. That one's easy peasy. Same idea with this last one, 9 plus 41. Is that greater than 9? Yes. Therefore, it can be a triangle. So, what kind of triangle is it? Let's take a look-see, right? Same color? Sure, yeah. All right, so 9 squared plus 40 squared. Is that greater than, equal to, or less than 41 squared? All right, so 9 squared is 81. 40 squared, we could almost certainly do that in our head, but just for proof and evidence, 40 squared is 16,000. 1600. How does that compare to 41 squared? 41 squared equals 16,081. You might be able to see what's going to happen. 1681. So 1,681. Now, you might be thinking, well, wait a minute. That's equal. That's not greater than or less than, right? And that doesn't match any of these things. Well, but they're equal. So what does that mean it is? Converse of Pythagorean theorem says that these numbers make a right triangle. Therefore, triangle is right. And that is it for that lesson. Did great. Easy peasy. We're going to learn about special right triangles in the next lesson. 30, 60, 90 triangles. 45, 45, 90 triangles. We're getting closer and closer to trig ratios. It's a fun lesson. It's going to be great. We'll see you in the next one. Adios. See you later. Sayonara. All the things. Bye-bye.